Hi, we are Namjo and Minseok from KAIST. We are here to present Metasurface, NextG-ready, µW reconfigurable mmWave Metasurface. This work was done under the supervision of our advisor, Professor Sungmin Kim. mmWave communication is a promising spectrum offering up to 20 times larger bandwidth than the traditional sub-6 GHz spectrums. 5G NR is already putting their efforts to leverage this wide bandwidth to enable high-throughput applications such as AR and VR services. However, in practice, mmWave communication suffers from limited coverage due to many blind spots. To solve this, Metasurface has emerged as an effective solution to enhance the coverage. Metasurface is deployed near the blind spots and reconfigures the beam from the base station towards the users. There have been a large number of promising Metasurface studies over a wide research community. However, the practical usability still remains a challenge, as they are non-real-time and non-compliant to the NR standards, or they need to be wall-plugged at high power consumption. So we present the Metasurface, the first real-time NR-compliant Metasurface at more than 2 years of battery lifetime for pervasive deployment. There are two major challenges in achieving real-time and NR compliance. First, to ensure the compliance, Metasurface should be reconfigured in real time following the beam management procedure running in the NR base station. Second, Metasurface should be tightly synchronized to be compliant with the symbol-level beam management procedures. Furthermore, all this should be achieved at µW power consumption. So to solve this, our design is twofold. First is the low duty cycle Metasurface in NR beam management procedure, achieving NR compliance in time configuration at µW region. Second is the low bandwidth asymmetric communication followed by the synchronization with multiple symbols, which achieves tight synchronization to the BS, again at µW region. So before we jump into design details on how Metasurface actually works, let's watch the real-time reconfiguration demo. This is the experiment setup, including a base station and the user equipment around the corner. In this scenario, the line of sight between the base station and the user is blocked by the corridor, which largely reduces the SNR. To solve this problem, we deploy our Metasurface at the corner. Metasurface will steer the beam towards the user to establish a strong link with high SNR and extends the coverage. Metasurface is a real-time reconfigurable Metasurface that tracks the user's movement and reconfigures to the best beam pattern in real time. Now let's see the real-time operation. As you can see here, following the user's movement, Metasurface is reconfigured to corresponding beam patterns and maintains high SNR. We will explain how it works step by step. Metasurface continuously measures the performance of each beam patterns, finds out and reconfigures to the best beam pattern. The user's movement is reflected in the measurement. Metasurface is reconfigured to the newest beam pattern in real time, and so on, and so on. As you can see, Metasurface is reconfigured in real time. Now I will explain detailed operations step by step. So Metasurface follows the beam management procedure, which is a periodic protocol repeating every 20 milliseconds in the BS. The following is an example setup. The line of sight between the base station and the user equipment is blocked, requiring Metasurface to reconfigure beam around the blockage. The first step is the beam sweep to evaluate the signal strengths of each beam patterns. Here, the base station first evaluates beam 1, beam 2. Then the Metasurface is reconfigured to continue the beam sweep from beam 3 to beam 4. The next step is the beam report. The user measures the strength of each beam pattern and reports the best beam pattern to the base station at the separate channel in the sub-6 GHz spectrum. Then the base station informs the best beam to the Metasurface, including the reconfiguration timing for tight synchronization with BS. The last step is the data transmission. Metasurface is reconfigured at exact timing to establish a strong link from the base station to the user for data transmissions. We know that Metasurface does not modify the beam management procedure, and furthermore, in achieving this real-time compliance with the procedure, we have found an interesting opportunity to reduce the power consumption, which is our first design. Here, we only highlight the inner surface operation. As we can see, reconfigurations are short, and hence, inner surface simply holds the beam patterns for the majority of the period. This opportunity allows us to implement low-duty cycling. To further reduce the power consumption, we designed a Metasurface that could efficiently hold beam patterns and low power. This is our Metasurface design, consisting of unit cells, each reconfigured by the vector diode. The vector diode does not consume power to hold beam patterns, as is capacitance. Furthermore, to hold a beam pattern, MCU can enter the sleep mode to reduce the power consumption. From this, our Metasurface can hold a beam pattern at extremely low power consumption of 72 nanowatts. As we implement low-duty cycling, we have achieved 2.1-year battery lifetime from a single AA battery. While the power consumption is very small, the Metasurface is sufficiently large for narrow beam reconfigurations. And so far, we have discussed how to hold the beam patterns in low power and how we implement low-duty cycling. We will now explain how the inner surface achieves synchronization with the BS and reconfigures in real time.
As he said, inner surface is designed to hold a beam in low power. From now on, I will introduce inner surface operation during beam reconfiguration. To following NR beam management procedure, reconfiguration timing is tightly synchronized to BS. In other words, the reconfiguration is finished in CP duration, which means synchronization accuracy should be under 260 nanoseconds. For this, we designed the NarrowBand Packet Unit, NBPU, and co-designed its hardware. This is new packet design is needed because NR-compliant synchronization is in low power is not able to with existing NR. NBPU is compliant to the NB-IoT, thus it can be embedded onto NB-IoT interface, which is already built in BS. On the other hand, NR surface use customized interface to reduce power consumption. When BS transmit NBPU, NR surface receive this and get the synchronization and reconfiguration information. Using the customized NBPU interface, NBPU has one significant property. That is, NBPU is an asymmetric communication having NB-IoT with 180 kilohertz bandwidth as the BS side, and the custom-built NBPU receiver with 15 kilohertz bandwidth at NR surface side. It helps reducing the power consumption with 12 times narrow bandwidth than NB-IoT. Now let's see the more detail about how NBPU works. The NBPU RX consists of the passive envelope detector and 15 kilohertz ADC. First, BS transmits the carefully selected NB-IoT symbol. Then the NBPU RX extracts its envelope first, then the sample the 15 kilohertz ADC. This means NBPU RX only samples once in the middle of the symbol. To maximize this symbol SNR, good NB-IoT symbol should be selected and set this NBPU symbol. Thus, we need to analyze which process has happened in NBPU RX. Considering NB-IoT transmit OFDM signal, we can express the signal shape of the envelope detector with the OFDM subcarrier phases. In other words, the envelope of the NB-IoT symbol can be controlled by choosing subcarrier phase combination. Thus, we can find the NB-IoT symbol whose envelope has maximized SNR. We will skip the details of the mathematical works in this presentation. For more details, please refer our paper. Instead, we will show our NBPU symbol design with examples. If we put unsuitable NB-IoT symbol, as shown in the uppercase, the amplitude of NBPU sample becomes very low. On the other hand, our NBPU symbol is targeted to maximize SNR, as we can see in the lower figure. Until now, we talked about how NBPU is designed for low power. It is quite impressive since this design shows 300 times power saving than the commercial NB-IoT. However, one of our goals, 216 nanosecond synchronization, is hard to be achieved with 15 kHz sampling rate. 15 kHz sampling rate provides 16670 microsecond synchronization accuracy, which is reciprocal value of the 15 kHz. 15 kHz sampling rate to synchronize with BS under 260 nanosecond, NRSurface wants 256 times more fine-grained samples. To solve this challenge, we utilize equivalent time sampling method. This is technique to mimic high-frequency sampling rates by repeating symbols. The repeated same symbol is sampled with slightly different time offset, where the amount of the time offset is controlled by MCU clock. In our implementation, we shift one tick of the clock, which is 223 every symbol. This time offset has the same effect as the sampling rate at 4.84 MHz. With this, NRSurface achieved under 234 nanosecond synchronization accuracy. We just want to remind you that our NRSurface is end-to-end NR-compliant Metasurface. Our Metasurface is reconfigured in time and hold them with low power. The specific power consumption of each step is 117 microwatts and 6.4 microwatts consumption. Also, the real-time NR-compliant design, NRSurface is received co-designed NBPU asymmetrically. With this, NRSurface achieves symbol-level synchronization within 119.3 microwatts. Then the power consumption of end-to-end power consumption is operated in 242.7 microwatts, which means NRSurface can operate 2.1 years with one AA battery. NRSurface is evaluated under various conditions. We will introduce some representative evaluation in this presentation. First evaluation we want to introduce is NRSurface under user mobility. In this scenario, BS and the user is blocked by a corridor, as we already shown in the demo video. We tested two user mobility scenarios, which is linear movement and the S-curve movement. Regardless the user's movement, the NRSurface provides good data SNR in real time, where the 19.3 dB average gain is achieved. Also, we test NRSurface under the blockage is dynamically changed. This commonly happens since our body also makes severe SNR drop in mmWave communication. We set the evaluation setter by locating metallic sheet around the user antenna. Note that metallic sheet works as only the pass-through the slit in the middle of the sheet. Then the metallic sheet is connected to servo motor to make them rotable. The rotation controls the possible angle, the possible angle of the arrival, which enforces the beam reconfiguration of NRSurface. With this blockage setting, NRSurface is located where it can provide multiple beam users. To test only Metasurface performance, the line of sight link between BS and user is still blocked. In this setting, the servo motor rotates fast the metallic sheet. The rotation is fast enough that changes the blockage environment in every beam measurement procedure. In other words, NRSurface should update its reconfiguration setting continuously. Here is the result of the evaluation. In this figure, NRSurface newly reconfigures every 20 milliseconds, which always provides the best beam. Thus, the user can receive best signal quality even in dynamically blockage changing environment. Finally, our Metasurface is suitable for pervasive deployment and can support multiple users. Please refer the details about this in our paper. In conclusion, we present Nrsurface, a new Metasurface that achieved 2.1-year lifetime on single AA battery, and real-time operation with NRB management procedure. Thank you for listening.